Hi everyone. One case of angular motion that's easy to analyze is rotation with constant angular acceleration, and that's what we'll look at in 10.2. The theory for this section is fairly quick, and then we'll move on to two examples. So if you remember when I first introduced kinematics in 1D, I introduced four kinematics equations that you can use to analyze problems with constant acceleration. Similarly, with constant angular acceleration, we have four equations that are the rotational equivalent to those translational kinematics equations. So these are for problems where alpha is constant angular acceleration, which means alpha equals d omega by dt. The rate of change of the angular velocity per unit time is constant as well. And you could integrate this and do some substitution in order to derive all of these, but we'll just look at how to use them. Okay, so we have omega f equals omega I plus alpha t. Delta theta, the angular displacement, equals omega it plus 1/2 alpha t squared. And then this equation without time, the third, omega f squared equals omega I squared plus 2 alpha delta theta. And the last equation, delta theta equals 1/2 omega f plus omega I times delta t. And I have omitted sometimes putting the z on the omega, but everywhere here this is omega in that z direction, or still perpendicular to that plane of rotation. All right, let's try the first example. The tub of a washer goes into its spin cycle, starting from rest and gaining angular speed for 8 seconds, at which time it is turning at 5 radians per second. At this point, the person doing the laundry opens the lid and the washer turns off. The tub slows to a rest in 12 seconds. Through what angle in radians does the tub turn while it's in its motion? How many revolutions is this? Okay, so this is a question with two intervals of motion, since we have two periods of different constant angular accelerations. So we need to find the angular displacement in each interval. In the first interval, we have the washer starting from 0, from rest, for 8 seconds, and then it reaches a final angular velocity of 5 radians per second. So with omega I, omega f, and t, we can use the last equation, number 4, to find delta theta. Delta theta equals 1/2 omega f plus omega I t. Plugging that in, we have 1/2 times 5 radians per second plus 0 times 8 seconds, which gives 20 radians for the first cycle. Okay, now for the second cycle of the motion, where it begins to slow down, we're starting with this initial velocity, or that final velocity now becomes the initial velocity, 5 radians per second, and this is for 12 seconds, and then it comes to a stop, omega final equals 0. So delta theta 2 will be 1/2 times this 0 radians per second plus 5 radians per second, and then times 12, the 12-second period, which is 30 radians. And to get the total, we just add them. Theta 1 plus theta 2 is 50 radians, and that can be converted into revolutions because the second part was how many revolutions is this. So we'll take 50 times 1 revolution is 2 pi radians, and so that washer cycle moved through 7.96 revolutions. Okay. Next example. You have finished watching a movie on Blu-ray and the disc is slowing to a stop. The disc's angular velocity at t equals 0 is 27.5 radians per second, and its angular acceleration is a constant -10 radians per second squared. A line PQ on the disc's surface lies along the positive x-axis at t equals 0. Part A, what is the disc's angular velocity at t equals 0.300 seconds? And B, what angle does the line PQ make with the positive x-axis at this time? Okay, and the line PQ is just along the x-axis to start. So we're looking for the final angular displacement in part B. But okay, let's look at part A. So again, I think it helps to make a list of all the known information. As the disk is slowing down, we have an initial angular velocity 27.5 radians per second. It's slowing down at a rate of 10 radians per second squared, and the sign is opposite as we would expect, right, to the initial angular velocity to indicate it's slowing down. And it does start at theta I equals 0, so just to draw it, it's starting right here at 0. 0 degrees, 0 radians. Okay, and then we can just choose one of those angular kinematics equations that works here. And it's the first one, number 1, omega f equals omega I plus alpha t. So we have 27.5 radians per second plus negative 10 radians per second squared times 0.3 seconds gives 24.5 radians per second at that point after 0.3 seconds have passed. Okay, then in part B we're asked what angle does it make? Starting here, the line is along here. What angle is it at to that axis at the end? So let's find the angular displacement. All right, so choosing a formula, there's more than one option, but I'll use the second equation here to find delta theta. Delta theta equals omega I t plus 1/2 alpha t squared. And then just plugging in what we have, 27.5 radians per second times 0.3 seconds plus 1/2, negative 10 radians per second for alpha, 0.3 seconds squared, gives 7.8 radians. Now you could leave your answer as 7.8 radians, but really since we want the angle to that line or to the x-axis, we should subtract. So 7.8 radians is greater than 1 revolution. If you calculate 2 pi, it's about 6.3 radians, 6.28 radians, I think. So we'll do 7.8 minus 2 pi, which is 1.52 radians. That's a bit hard to estimate, so if you convert to degrees, so multiply by pi over 180, we get 87.1 degrees. So at this point, it's gone all the way along here, one full rotation, and it ended up almost at 90 degrees. Okay, left hand is not working there. So it ended up even closer, really close to 90 degrees at the end, 87.1 degrees. Okay, that's all for this section. We'll go on next to relate these angular quantities to linear quantities.